if you look more recently, it's lots of stories about what went on in this most recent financial crisis. Plays off notions of sentiments and caution and fear and the like. To some, it's the thing that leaves me a little bit cold about those discussions is there's little empirical content attached to it, or little discipline to it. Yes, we can always kind of make up beliefs, but we really want to have a set of tools in which we can think about how to quantify, calibrate, or think more systematically about the kind of these concerns about not knowing models, not knowing probabilities, and the like. So this is kind of what we're about, and kind of what I want to talk about today are some issues that come in terms of trying to measure or say calibrate some of these notions of ambiguity, concerns about robustness, or the like, which we find to be very interesting, intriguing, and attractive. Now, this whole literature on risk and uncertainty, ambiguity, concern about model misspecification, and the like, is going to break apart these two different steps, and that's going to be really critical. We're going to be thinking differently about risk condition on a model from uncertainty across models. And we're going to think about decision makers as kind of really confronting these in rather different ways. We're going to be all about how to parameterize this and how to think about disciplining those parameters. So we're guided by applied work. We want to do things in tractable ways, in ways that we can think about implementing in practice. We don't want to get rid of probabilities completely. In fact, the more recent versions of robust control theory don't either. So we want some baseline probability assessments, but we don't want that to be the complete end game. We want to do robustness in terms of the assignments of probabilities there. So we want to look at robustness when, suppose we want to assign uncertainty across models. We want to have our decision maker explore with what are the consequences of those assignments of that uncertainty. How does that alter the decision problem? And do explorations like that. In a lot of economic dynamics, there's a limit that people take, which can be revealing sometimes, and it's to go from discrete time to continuous time. Now, there's been kind of a criticism of this whole ambiguity literature about, well, if you take continuous time limits, it's kind of things, its potency gets removed. And so I want to readdress this question and kind of help us think more generally about these issues of measurement and calibration. If we want to learn about iota, I need to form a likelihood. That's how we typically do learning. We construct likelihoods as functions of this unknown parameter here, iota. Here again, this continuous time limit does some funny things in the sense of I can figure out this variance locally by just looking at observations very finely, and that would reveal the parameter value. So to make the estimation problem challenging, the challenging part is estimating this piece here. So really what you've done here is the following, and this is what is either intriguing or peculiar about this continuous time limit, is sigma's the same even though I've reduced information. I've reduced compound lotteries here. So yes, I've changed this I had to change this object, but the amount of risk locally that shows up is going to be quantitatively the same because this has the same covariance structure as before. It's the same sigma that shows up here. So taking this continuous time limit, locally, the amount of risk remains the same. This has some rather spectacular consequences. Estimation error is just not consequential there as a consequence of this, which is truly bizarre, right? I mean, it seems like there's a econometrician struggling to estimate iota, but its consequences are so subtle locally that it leaves in place the original risk-return trade-offs. A Bayesian learning story doesn't alter risk-return trade-offs, which is and so the type of stories that we want stories that under which estimation really has much more potent consequences. One of the criticisms about this so-called smooth ambiguity story just has to do with the fact that once you make this observation, anything you do about simple risk aversion over here doesn't have much consequence. So when we want to talk about putting alternative models on the table, we want to ask the following question. Okay, imagine a decision maker. He's going to focus on say, one particular class of models. But we're going to have him search the consequences of other models that are not too far away statistically, that are ones in which would have a hard time telling apart given historical data. This turns out for us to be a very tractable way to, once we start exploring misspecifications of actually both types, once we explore misspecifications here, we're going to look at misspecifications whose log likelihood ratios are small. So we're going to imagine our decision makers, if it were some model that was just blatantly different from the one that he's looking at, he or she would have figured that out easily. But we're going to leave on the table models that would be very, very challenging to figure out. So in effect, in continuous time, you have this huge penalty associated with changing things, with very little consequence. Okay, so it's more kind of a corollary of the same thing. Is that any misestimation or any misspecification of these mu's is really, in that sense, quite subtle. And so one way around this, it seems kind of obvious, ex post, is you take penalties like this and you scale these by the sample interval, by dt as well. Since this is scaled by dt, we're going to have to penalizations like this have to be scaled by dt. That has ramifications for how you measure these parameters of ambiguity, for these robustness parameters as well. You can't really think about those parameters fed to these models as being independent of things like sampling intervals. Imagine computing a continuation value for some plan, consumption investment plan, that actually in this case depended on, say, on iota. We go under we say, well, suppose I knew what iota was, and let's figure out the corresponding continuation value, kind of condition on that. So we do continuation values conditioned on not only that the history of the data, but also the unknown parameter. And then in the current period, we take that continuation value and we make a robust adjustment to it. We say, well, from that continuation value, now we look at the consequences of kind of changing the posterior over the parameter iota. Since we're not just looking at an increment now, we're looking at the entire future of this consequences of this plan. There's no need to do the scaling, which we talked about. The scaling by the sample horizon doesn't matter anymore. And this is the corresponding continuation value. It's got these two different sources now, misspecified dynamics and misspecified state estimation, but you don't have to engage in the scaling here because now the potency is there because you're looking at the consequences for the entire future plan of kind of changing this, changing your estimate. So the single decision problem, strictly speaking, has to become a game a person plays with himself in order to confront changing tastes. But this is fairly standard in the decision theory literature. So anyway, this changes the consequences of the misspecified estimation by not just looking over what happens over an increment of time. Since you're conditioning the continuation value on the object you're trying to estimate, that increases the potency of changing the posterior distributions, or the consequences of changing them. I've talked about this all in the context of a pure estimation problem. What we're really interested in are these hidden state Markov chain models, under which there's a state which is moving around over time that's not directly observed, and you're trying to track that state given historical data. And these methods are extendable to that case in a direct way. But the important thing is this notion of statistical detection likelihoods give us a different vantage point on how to do this kind of calibration of concerns about ambiguity, model misspecification, or the like, and they lead us to address some things like scaling issues, which at least elsewhere in the literature we found to be a bit confusing.